Hi, I'm Daniel and welcome to the video series of how to define the VMID for advanced mill-turn machines. Since this is the first video in this series, I would very like to start off what is in general the VMID, and we'll start with one very simple 5-axis mill-turn machine which has the turning capabilities, and I'll start to define basically everything from beginning to the end, taking care about how to do some steps and how to define some of the parameters, which is very important in order to run the mill-turn module. So first of all, we'll start with the definition of what is actually the VMID. Then we'll go through the analyzing a little bit machine kinematic. We'll add some axes and devices, show a couple of the options, how to set up, where is the part, where is the tool. I'll show you also how to setting up the axis limits, one of the very important parameters. And then we'll go towards how to set up the drive units on the table and the spindle, definition of the submachine, how to set up the first angle pair interval, axis order, and very last one and new parameter is how to define the tilting turning plane in mill-turn module. Okay, so what is in general the VMID? So the VMID, or the virtual machine ID, it's actually the internal SolidCAM application that where you can actually define or describe some mechanical elements, and we are calling it devices and its kinematic relations. Now the VMID has the big influence on the later on CAM part definition, in the machine simulations as well, operations including also the MCO and the G-code generation. Now let's check it out, what we have over here. First of all, I'll just jump into the folder which you basically get it, and over here what I have is the first folder that you can see is the Mazak i700T, which is basically the machine that you can see over here. Let me just open the machine simulation. So this is the ready machine simulation, and let me go to the front view and let me fit it. So basically this is the machine that it's a simple table 5-axis milling machine, but since it has this T, it represents that this machine actually can perform also the turning operations. I choose this one because I found it very interesting for the very first video in the series of those videos. Alright, so let me go back to the folder itself. So the first folder is the folder where all our STL files are located regarding to the machine that you actually see in machine simulation. The next one is just the material database that we are using in this demo part that I'm going to use as well over here. We have our VMID that is already done, and we have some of the PDFs that it's very important before you even start to define the VMID for this particular machine. I'll just open those in a couple of next minutes. Alright, so let me go to SolidWorks, and let's open the SolidCAM settings. Since I'm using this VMID and my STL folder, it's located in some specific folder, I would like just to copy this link over here, and let me go back to my SolidWorks and to the SolidCAM settings, where the very first thing what I would like to do is to change my default CNC controller, because over here probably you will have everything as a default, but I would like to use some specific one. And once I did that, I would just like to refresh everything, and over here I will have mill-turn CNC controller with specific VMID name. Alright, the same thing I'm going to do for the machine simulation, since I would like to read the folder that is in this in this link, okay? And I'm going to click OK. I'll just now open the demo part and click OK. Alright, so what we have in front of ourselves is just a simple 5-axis part that has also some of the nice surfaces that can be done with the turning. We have a nice fixture over here, and to open the VMID, you would find it in the very second icon just below the CAM part, where we have the machine, and in parentheses is the VMID name itself. So just double click on it, and let me just very quickly explain you what you have in front of yourself. First of all, I'll start with the drop-down menus where we have the File, Open, View, and Help. And basically this is the very standard commands that you will see in any application. Some of those it's a little bit extra, and I'll explain it in some future videos. Then the next thing what I would like to show you is that every VMID will have these 4 tabs. The very first one is the machine definition, which in most I will cover it in this video, and it is the tab where you can define the kinematic relations of your specific machine. The next tab is the controller definition. Then we have something like user-defined parameters that later on the user can use, and later on also in your post-processor. And also we have the working style. Generally, how basically would like to get the G-code output. Alright, now the very first thing before I start to define the VMID, I'll start with analyzing the kinematic of the machine. So in this case, I'll open machine simulation, and the very first thing what I'm going to show you over here is that we have this machine has the 2 rotary axes. The tilting it's A axis, and the rotary one is the C axis that is on the table. And over here we have 3 linear axes, which is on the spindle itself, which is actually the X, Y, and Z. Now of course over here you cannot see where the axes are located for a simple reason, because I didn't open the STLs itself. So I would like to show you in this moment the tool that I'm actually using. It's completely free. It's called 3D tool, and it allows you actually to open the generated STL files and to see where the coordinate system of those STL files are located. And let me just hide this geometry, and the very first thing what you can see over here is that this geometry has the sliders over here, which actually represent the y-axis, as you can see it over here. So the first linear axis is located on the spindle, and therefore it can move along the y-axis. The next one, the green geometry, represent the x-axis, as you can see with this yellow vector. And the third axis is the z-axis, and it's located over here. And it's very important to follow the rules of how which axis is actually first, and which axis are actually the child of the previous axis itself. All right. Now if we know this, we can start with the very first moves and definitions of our VMID. Let me go back to the SolidCAM. Alright, because I already have defined the VMID, I would like to start everything from the beginning. To do that, you can go on the very first icon which says New, and I would like to do that. The first thing is that our machine will change the name, and also we'll already get something in our VMID definition. So it's not possible actually to start everything from the zero. The minimum that you will get in the VMID is the spindle and the table itself as the minimum parameters and devices that every VMID needs to have. Alright, so let's start with the definition of the axis. So how to add the axis, or either any of the device that you see on the left side of your panel. You can go right click, do a right click on the machine, and here you can add any axis or any device that you can see over here. As well, one of the ways how you can do it, you just simply click on any of the axis itself, and you can do the same thing, just do the right click. As well, one of the nice ways how to define, for example, the spindle. Let me just show you this. I will just, of course, I have to remove the submachine, and over here I'll just remove the spindle itself. And over here you have the device panel, so you just can do a drag and drop to any of your axes. So okay, so let me start first with the linear axis. So as we saw in the few minutes ago, the very first axis is our y-axis, and then we have our x, and then it's a z. So the structure is very important. Therefore, the first step what I'm going to do is I'll take my y-axis and I'll use drag and drop to machine itself. In that way, my first axis is going to be the y-axis. Then I have the x-axis, which is actually now single one over here. So I'll just use drag and drop and move it to my y-axis. This will make the structure as actually we need it. And then we have after our x-axis, we need to have the z. So I'll just take the z-axis and I'll use the drag and drop over here. And this is actually the result that I would like to get. And after the z-axis, I have the turret, and I'll call it here the spindle. Okay. And that's it. Now I'll start basically with the rotary axis. So very first one, it's our a-axis, and after that we have the c-axis. So I'm just gonna do the right click, and I'll just add an axis. This axis will be called c-axis, and after that we'll have our table. I'll stop here at a moment, and I skipped one thing over here that I would like to start from the top, maybe just to explain you a few more things about what we have under our machine. And I'll click on the machine itself, and here we have some of the basic informations regarding to our VMID, which is the catalog number. Here we have the company, so we can just type it's a Mazak itself, and the model it's y-axis, it's i700T. And also here we have the controller, which is the matrix 2. And basically this is the very basic information that doesn't have any influence to the G-code itself or either of definition.com part. It's just the information that the post-processor developers can use, in order to understand better what machine is about. Alright, now over here what we have is the operation type. I would say very important parameter which is telling us that what this machine actually can do. So if we choose the milling, machine can only perform the milling operations. If we choose the turning, only turning it's available. And we choose milling and turning, then both operations can be defined with this VMID. Alright, so because this VMID series is about mill turn, and machine itself it's a mill turn machine, I'll just click milling and turning over here. The next parameter is the post processor, which actually will read the folder that we just selected, and over here we would be able actually to select the GPP file, but since we don't have any in the folder, none will be listed. Basically, this VMID will read the GPP file, which together of those two represents the post processor itself, very necessary for G-code generation. Over here we have machine simulation name, and because I already defined also the VMID and the STLs are already defined, so what I'm gonna do in this moment, I'll just go to my folder over here, and just what I'm gonna do, I'll just copy and paste this, and I'll change the name just to i700T. Just remember this, that the name is very important. And once I go there, I'll just remove this XML file. You'll not have to do it, basically you will not get it on the very beginning. Alright, so now I define this folder. I'll just go back to the SolidCAM, and now in the machine simulation name, basically we'll connect our VMID to that specific folder, which will be very important for every time when you run the machine simulation. It will read this folder basically. So now if I click on the drop down menu here, the i700T and MyZig i700T folder is listed. So just select this one, the very new one that I actually generated. Alright, let me go just to the options, and for the options of the table and the spindle I'll talk a little bit more later. And now I'll talk about machine orientation. Machine orientation is just a simple parameter where we can actually control how the user will see the machine in the machine preview window. What this basically means: if you are in the front of the machine, how the coordinate system is oriented on this machine. As you can see on the left bottom of this VMID window, you can see that Z is going up, the X is going on the right side. So this is a simple, like it's on the simple 3-axis machine, and most of the 5-axis machine has this orientation itself. But if we better look on the mill turns, the very standard mill turns has different orientation. So if you are in front of the machine, the Z-axis is where our X is, and our X is where our Z is, and Y is basically switched to the different orientation. So therefore, if I just go to our preview, here I can see that our Z is going up and X is going to the right side. If I would like to use the mill turn for the most of the machines, I could do this. So my X vector is actually my Z, my Y is actually switched, and my Z is actually X. In this way, if I now click to the front view, you will know the orientation is actually changed to the very standard orientation of the all mill turn machines. The example of today's example is totally different. This machine is 5-axis milling machine, but it has the turning capabilities. Therefore, I'll just not use this one. One more thing, I'll just move this back. I would like to show you that this rotation around degrees, you can just type here the values that you would like to rotate this coordinate system, and not use these value vectors. You can do it in both ways, it's up to you. But once you change it, if you've done everything correctly, in the left bottom side the picture will be presented, and now you can see the Z is going to the where it was the X, and X is going where it's the Z, and Y it's switched. Alright, now I'll move back the values that it was, and I'll click go to the front, and now we'll see that we have the orientation like on the simple 3-axis milling machine. Alright, I'll just close the machine preview for now, and what I'm gonna do here, I'll just save this machine. I'll just put some name, probably not the same as we have it over here, so I'll just type MyZig i700T, and I'll just do a save. As you can see, still we are our project is not using this machine, so therefore I'll just save and exit. Of course, I need to add some submachines, but later on we'll just select this particular VMID to be used in this project. Okay, so let's focus now on the kinematic of the machine. First of all, the order is completely fine. Just what I would like to have is first linear axis and the spindle itself, and then the rotary axis and the table. So what I can do is just move the A axis to the VMID itself, the icon, and that will actually bring my axis to the very bottom. Okay, so let's get started with first linear axis. If you click on any of the axes, this is what you actually will, this is all the parameters that actually you need to fill in. And the very first one is the name itself that will be listed in every simulation. Then we have the axis type. There's two possibilities of, two types actually of the axis. It's the linear and the rotary itself. This one is linear, so I'll keep it. Here we have the axis vector. Axis vector on our machine, it's on the y-axis and it's positive. Now there's some rules when it's negative. This doesn't affect to the G-code itself, but only effects on the machine simulation. So let me just go back to my presentation just for a moment. Alright, so the definition of the vector. So there's one simple rule. If the linear axis it's located on a spindle, then the axis vector will be always positive. So as you can see on the right video, the tool is going from the x0 towards x50, and the vector is actually positive, and in this case the spindle is moving. Now in this example, if we have the axis that is on the table, which means the part is moving, even if our G-code is going from 0 to the positive 50, the vector will be negative. Therefore, the negative vector has to be defined in machine simulation. Okay, so let me go back to the SolidCAM itself. In this example, all our axes are located on the spindle, so therefore all will be positive. So let me go to my X, it's X over here, and Z it's over here, it's fine. Okay. The next parameter is the home reference, and the home reference is the parameter which actually indicates where what is the initial or home reference value for the y-axis, or what is the parking position before you start the machine simulation. In this example, I'll just jump to my 3D tool. You will note one thing here, the spindle itself, it is located in machine 0. And I didn't mention this, but the coordinate system of the STL files are located in the machine 0, and our spindle itself, it's located in that point. So I'll choose that this is my home reference point. Therefore, the home reference for all my axes will be 0 itself. Maybe this is the right moment now to show you the very first PDF file that I have it in a folder, and this is the first one. And the very first thing what I would like to pay attention here is this document. It actually will help us to put some of the rotary axis pivot points over here to better understand where machine 0 is, where is the point of rotation and tilting, some of the values that we'll need to put there. And the very important also information here is that this specific machine can have three different table geometries. Here it's marked like 13, 14 and 15 in the part table, and in this example I'll use this tab 630 millimeter table, which is located over here. Alright, let me go back to SolidCAM. Okay, over here now we have the minimum and the maximum limit. So how we can know this? Of course, every machine has this the linear or rotary axis different. This depends on the machine itself, the machine brand, and etc. I'll just open now next document, which is called the stroke PDF. And over here, this document, it's actually really nice because it has the diagram over here, the drawing of the machine where our spindle is located over here, machine 0, and it has some of the very important points. This one is the where our stroke of the z-axis is, for example. Then we have the center of the a-axis, and so on and so on. Also we have for the c-axis the same information. So what I'm going to do here, I'll start for the search for the our model name, and here it is. We have it's the 700T, where our x it's minus 630, our y it's minus 1100, and our z is only 600. So pay attention that those values are actually coming from the machine 0 itself, where actually our STL and everything is respecting to this coordinate system. Therefore, I'll just jump again to the SolidCAM and I'll define this. So our minimum on the Y, it's 1100, and our maximum, it's 0. On our X, we have minus 630, and our maximum it's on 0. And our Z, it's minimum it's minus 600 if I'm not wrong, and maximum it's actually 0. Now what that means actually, if I just again open our STL, you can know that this machine cannot go more on the X, cannot go more on the Y, and cannot go more on the Z. So it has to go in the negative, respecting to the machine coordinate system. Alright. Let me go now go to the A-axis, and following the rules that I've explained a few moments ago with the linear axis, negative and positive, you can know that those two axes are rotary axes, and they need to be, since they are on the table, it means that this vector will be negative. Now in the most of the cases this will be a good definition, but some of the machine brands will have this vector of rotation on the rotary axis can be switched in the different direction. Alright, so I'll go to the A-axis, and this axis it's rotating around the X in the negative, and our C-axis over here it's rotary, and it's also rotating around the Z on the negative. Let me go to the PDF, and over here we have a maximum and a minimum. Our C-axis can go 360 and also into infinity. Let me go to the SolidCAM to find that. Okay, so it can go minus 120 and maximum 30. And on the C-axis we can go to the well, this definition is fine. It's infinity. Alright. Now here we have the rotation point, but I'll come to that definition very soon. Now we have over here the interpolations tab. So this is the minimum digit that it's actually represented by the G code. So you can see it have the influence on the number of the digits in the G code. And the very last three parameters it's respecting to the rapid, the minimum feed, and the maximum feed. All those informations are actually located in the same PDF that I show you over here. So let me just try to find it. Okay, it's this is T, this is for the turning. Maybe no, it's over here. Okay, so here we have the rapid feed rate, and for the X, Y, and Z, it's almost the same. It's 60,000 minimum millimeters per minute. So I'll just define that. So I'll go to my y-axis, and my rapid it's 60,000, right? And now I would just like to show you one very nice feature. Once you define this, you can go do a right click and apply for all axes that are actually connected to this one. You can know that X is different. So now if I do a right click, apply it, you will know that it applies the same rapid parameter to all of those. Very nice option. This one is I think it's different, so it's 56,000. Let me go back again to this. For the A and C it's 18, but sorry, this one it's 18, this one is 36. So let me just define that as well. So 18, and this is yep. All right. Now let's define the working feed, maximum and minimum. So let me go to that, and we have the cutting feed rate, and for all of those axes are 8,000 except of those two, which is actually 9,000. So let me define that as well. So the minimum is 0 and the maximum is 8,000, and I'll apply this for all. This one is 9,000. Alright. Perfect. Now before I continue to our devices itself, first we have to define the rotation point. So what is the rotation point at all? I'll just go to my 3D tool. If you note here, we have our machine coordinate system, but our rotation actually it's over here. So we need to find that point as well for the A-axis as well for the Z-axis. Where we can find these values. First of all, there's two ways how you can get it. The first way it's just we can just simply go to the measurement tool, and I can search for this point over here, and then I can just select it over here, and here I can clearly get these values. Now this is the one way. Just pay attention that those values over here, what you can see in this tool, it's all positive, or actually they are all absolute. But if you respect the coordinate system that you can see, you can know that it's going into negative x, y, and z. So pay attention about that. Another way is you'll basically get into the documentation itself, and in this case I'm gonna use this one. So I'll just go to my I series of T. Okay, perfect. And over here I have the A-axis center on the Y and over the Z. So it's 650 and 600. So let me define that. So my A-axis first. So minus 650, and on the Y it was minus 600. The X is not important to define since our vector of rotation is around the X. Let me go to the Z-axis. Let's go back to the PDF. And here we have X and Y. As you can see, there is no Z as well over here because the Z-axis is rotating around the Z-axis. Alright, so here we have minus 600 and minus 350. Okay. Minus 600 and minus 315. Alright, perfect. Already in this position, I can go to the preview itself, and I can know that those two axes are defined, and we can clearly see it over here. We can also use it to see is the rotation correctly defined. Perfect. Okay, still we didn't finish. I'll just, in this moment, I'll hit save button. Okay, now we can start play with the spindle and table device itself. So what those devices actually are. So first, the spindle is the device where our tools are located, right? And the table is the device where our part is located. So those two are very necessary for every VMID. So I'll start with the spindle itself. I'll click on the spindle, and over here I have the spindle name. So this spindle name is just optional, and you can put here anything what you want. Immediately you have the tart number. This number will be also presented in the G code if you would like to use it. Catalog number, very optional, you don't have to define anything here. We have the options. If you do a double click on the options itself, it will drop you to the options over here, the parameter that we have. Now the SolidCAM support 3 different turret types: the spindle, linear, rotary turret, and that's it. In this particular case, I have my turret type, it's actually the spindle itself. Now the next parameter is minimal angle step around the spindle axis, where it's a value that actually it's used then for the multi-tool holder. Now if you put 0, it means that it cannot be used. If you put like 0.01 over here, it means that can go almost, you know, to any angle. And if you put here, for example, 1 degree, only 1 degree of in this case can be used. So in this case, I'll just put here like 0.01. Next parameter, it's regarding the position or where the tool check will be executed. Next, the tool change time. Over here, I'll put just like 6 seconds. This parameter will directly affect to the cutting time that will be calculated during the G-code generation. And here we have something like a number of the tool in the magazine. This particular machine can have only 30. Number of the tools in the station, it's at this moment it's 1, and we have number of the axes that is using this device is 3. Alright, the next parameter is options. As you can note, the options is available also on the Spindle table and in general machine itself. Now let me just go to the presentation in this moment, and let me go back here. And this slide is just that all those device options that we have here and machine options, you can define, actually you can control those parameters later in the tool parameters or either on the any MCO operations. And that's like the coolant, flood. You can turn on and off some of the devices on the machine itself. Very useful for this demonstration and this video. I will not set up here anything specific. So let me go back to our VMID. Maybe, why not, I'll just put the flood. Maybe I would like to allow the, I don't know, spindle orientation. Very maybe here I'll put very important parameter over here for the spindle, and in this case it's to allow the tool to be in reverse position. I'll show you this feature a little bit later, so just allow it. Okay, over here now we have I'll skip a little bit the coordinate system at this moment, and here I'll talk about the drive unit. The drive unit is available on the Spindle and as well as in the table, and it basically means, do you have a live tool on the Spindle itself? If here the active is set to no, it means that only turning tools can be used. Our particular machine can do both, so I'll just click yes. Now here we have a very nice option. We can set up multiple number of the gears that this spindle has. This machine can go only to the 12,000, so I'll just put it here. We can put the minimum I think it's 50, and the maximum is 12,000, sorry. The power here in the kilowatts, it's just optional, it's just information only, it's not taking into account anywhere, okay, so it's just, you can put here anything. In the future, this parameter will be very important and will be used for example, the eye machining. I'll click OK over here. Let me go back. Let me go to the table drive unit. The table drive unit directly describes that can our part have rotations. Okay, so it's not about can we use the A and C axis, but can we use the rotation, or in a simple way, can we use the turning on the table? That's our table can have the turnings. Yeah, so in this particular case, this is very important option. And over here we have the same parameters like the number of the gear, the gear itself. So I'll just set up it's to 1, but usually some of the military machines, very high, have at least 2 gears. So very useful to use later on in the post-processor. In this case, our gear 1 it goes from 0 to 4,000, which actually it's you're getting here as a default. But if I go to our PDF, I'll just go to a little bit bottom. I think over here is the I series, this is the T series. You can note here that we have the turning spindle and we have the milling spindle. Our turning spindle can go up to 1100. Okay, and this we have the standard of 35 to 18,000, so I'll change that now. Alright, and 11, very nice. And let me go to the drive unit itself and let's change this to the 35 and 18,000. Perfect. Now an additional parameter here we have the rotation vector. This parameter is very crucial for determining of clockwise, either the counterclockwise rotation on this table. So if the rotation of the clockwise is determined by the z-axis and follows the milling, then this vector will be actually positive. In most of the cases, this vector on the main spindle, for example, is always negative. Okay, so also in this case, also in this machine, this rotation vector is negative. All right. Now let's talk a little bit about the stations and its coordinate systems. So what is actually the station on the spindle, and what is the station on the table? The station on the spindle itself represent the tool, actually where the tool will be mounted. But the position of the station is relative to the coordinate system of the device itself. In the same way, on the table, the station on the table is where our part is mounted, or where our machine setup will be actually calculated or mounted. Okay, so very important positions, very important for the VMID definition. Therefore, I would like to open the 3D tool, and the position of our tool, you can know that it's located over here, which means that the coordinate system of our spindle is located over here, so I don't have to change it. It's actually in the 0 itself. But our part, it's actually located over here. Therefore, I would like to measure that. I'll go to the measurements and I'll just click over here. Let me just maybe I can just remove this one, and if I click over here and let me just click on the spindle itself, let me just delete all again, sorry about that. Okay, we have 700 over here perfectly. All right, so the station coordinate system, I'll just name this station as this one it's a tool, and this one it's a part. You can name that whatever you want, it's up to you. Make note that on the spindle itself we can have multiple stations. Okay, so the coordinate system, there is coupled with the coordinate system spindle rules that I will cover in some of the next videos. In this case, I'll just leave it as it's 0, and as well on the tool itself it will be under 0. So far I'll just change the coordinate system of the table. Now I can leave the coordinate system to be a 0, 0 and just remove our part position, or I can just change the table coordinate system over here and leave the part station to be 0. So it's up to you. Okay, so I'll just go to the coordinate system over here and I'll put my z on -700. On the y, if I'm not wrong, it was -600, and on our x it's on -315. Perfectly. Alright, I'll just go to my tool itself and I'll talk a little bit more about parameters that we can see over here. This is the station number, station name, default tool direction is what is the initial state of our tool direction, and by default it's set up to the Z, which one is correct for this machine. And I'll talk about this parameter a little bit later in more complex military machines. Coordinate system itself is just, if you double click it, it will bring you to this one. Now the drive type. Every specific station can have different drive type respecting to the drive unit itself. So if we set up to the not driven, even if our spindle is set up to have the engine or transmission, it will not use that one. So over here we have a couple of the options. It says it's not driven, which means only turning tools can be used. We have the cell drive, which means that we have additional drive unit only on this station. Then we have a gear, which allows us to put the ratio over here. And then we have director of the drive unit, which I'm basically going to use that one, and it will use the drive unit itself. The adapter type, you can specify the adapter which will be a default later on in the definition of your operation. And here maximum position letter is the parameter which allows you to put multiple positions in the same tool position. This parameter is very useful for the rotary turret tools and for the holders that can hold more than one tool. I'll talk about this one in some of the future videos. Alright, the same on the station of the part. I'll just say direct from the drive unit itself, and that's it. And I'll save. And the next topic, it's definition of the submachine. So what is actually the submachine? The submachine, if I click on this icon over here, you can note that it allows us actually to determine the active cutting pair devices. Actually, it needs to be the spindle and the table combination. So actually the tool and the part itself. So to add the submachine, you have to go to do a right click and add a submachine. Over here the submachine is defined, and over here we have some of the options. So let's start with this. First of all, we need to define the two devices. The first one is the turret and another is the table. By default, since we only have those two will be automatically selected and none of the others will be listed over here. Then we have the name, so I can put any name over here as a 5-axis or anything. The submachine name will be changed. Over here now we have operation type. It's very useful for the advanced military machines because then per submachine we can change the operation type that this particular submachine can prefer. What that means? That means if I have a complex advanced military machine, for some submachines I can say that it's only capable to do a turning. But pay attention that this parameter is directly connected to the machine operation type. So that means if my machine can only do a turning, that means that my submachine can only then perform a turning. Only if my operation type is set up to the milling and turning, I'm allowed then to control. Either my submachine will be capable to do a milling, turning, or the both. In this particular case, I will use both. Max inverse time feed, if you want to define it, you can define it over here. Here we have MRZ point. This is the cross-section point of the A and C axis. It's just grayed out because it's calculated according to the coordinate system that we defined over here. And sorry, it's the point of the cross-section of the rotation point and its vectors. Okay, so let me go back over here. And now we have the first angle pair intervals. As default, the VMID will calculate this automatically. So over here, if I just do, we can set the interval of the minimum and maximum, taking care these values are taking the values for the tilting axis. Let me just open the presentation itself. Okay, so as you already know, every SolidCAM milling operation has, if you go to the motion control, has this 5-axis option, which will actually determine it in which angle pair you would like your angles to be calculated. You need to define the interval of your tilting axis, and as you can see, I would like always to get from my 0 to a 120 to all my angles try to be in this interval. So this is my first angle pair interval. And my second angle pair interval, if that is possible by generating by generated angle, it can also go over here for some of the angles, and of course the user has to select second angle pair. This is very useful for the machines that can perform 120 degrees angle in the both ways, and very useful for especially for those machines who don't have too much Y stroke. Okay, so in this case it will be crucial. Perfectly. Let me go now to the coordinate system itself, And what we have over here is just the position that is automatically calculated since SolidCAM 2016 and 17. It will respect the table coordinate system and the part coordinate system position. It will calculate the both, and he will put the position of where our part is mounted for this specific submachine. The coordinate system vectors of specific submachines will be covered in future videos. So far I will not explain that in this one. The parameter that we have over here is the axis order, and SolidCAM has will allow you to actually select what each submachine, which of the axes that are defined in this particular VMID with selected devices, which can perform which movements. This is very crucial for the machine simulation as well for the G-code generation. So over here we have the values for the Y, X, Z, A, and C. As you can see, it's automatically selected and choose the proper one. Now over here we have the second, first, and third rotary axis. So there are some rules which one is the first rotary axis, which one is the second rotary axis. So let me go back to the PowerPoint, and over here we have, for the different configurations of the 5-axis machines, we have a table where both rotary axes are on the table. In this case, the second rotary axis is the tilting axis or the A axis, and the first rotary axis is the C axis. The second rule, if we have the head table machine, in this case I just used the Milter machine, where the B axis is on the spindle and the C axis is on the chuck or on the table. In this case, the first rotary axis is again the C axis, and the B axis or the tilting axis is the second rotary axis.
And the third one is the head-head kinematic, where the C axis is the first rotary axis and the A axis is the second rotary axis.
Alright, perfectly. Let me go back to the VMID itself. And over here we can define all of our axes, how it can be used in the milling as well as the turning. The available options are simultaneously, indexial, or not even used. So the milling, all those 5 axes are simultaneously so as it is, and I would like to be in that way. In my turning, my Y axis is only used as indexial, X and Z it's always simultaneously, and my A axis it's used, maybe I can use also this simultaneously, it's used indexial, but my C axis is not used. So I'm not using the C axis milling, C milling axis in my turning at all. And over here we have inclined turning. In inclined turning will allows us to choose our A axis to be simultaneously, which actually will allows then the user to define the turning operation with the B axis simultaneously. In this particular case, in this machine, this is not possible, so I'll just keep it as indexial. Alright, and the very last thing what I would like to show you in this video, it's the special parameter that we have in order to define the tilting turning plane. So what is all about? So let me open the document that I have here. Is the very last one. It's the turning plane itself. And if I do that, this simple document represents actually that it's telling us how the coordinate system is actually orientated for the milling and the turning respecting to the tilting axis. In this case, if A is 0, the milling, it looks like on simple 3-axis machine, right? But if you turn on the turning mode, it will automatically rotate the coordinate system in the positive 90 degrees. Right, so if you take the right hand rule around the z-axis, it will rotate it. Now if we have the a-axis, if it's minus 90, then again it's just rotated 90 degrees over here, as you can see it over here. Alright, so this machine can perform the turning only on A0 and A minus 90. So how to define that in our VMID? So let me go to the VMID itself. First of all, if your operation type is milling and turning, it will allow you to define this feature. You just need to do a right click on the submachine itself, and you can here add a turning plane coordinate system. This will allow you to actually rotate the submachine coordinate system defined over here around the z-axis. And over here what we have is the rotation rules. Just remember, we have here a couple of the rules. The first rule is that the turning is only possible in A0 and A minus degree and minus 90 degrees, right? So everything between is not possible. And the second rule is that for both of those possible positions, the coordinate system has to be rotated on the 90 degrees in positive. So let's see how to define that. So what I'm going to do here, I'll just double click on these rotation rules over here. This will allow us to define those rules. So let me go over here and I'll click on A axis. Since I just click on the A axis, already some of the rules are already predefined as a default. So is it correct? I will not say so. So we need to modify it a little bit and to apply the rules that we have. So first, this is the A axis, and this is what is the minimum lower limit and what is the upper limit, and what is the status, is it possible or not, and this is how much you would like to rotate it. Okay, so we have from minus 120 condition if it's less than equal than our first stopping point, it's minus 90. This position from minus 120 to the minus 90, it's not possible. So I will not allow turning operations to be defined in this angle. So I'll say it's illegal. Now to apply more rules after this, what you have to do is just click on the first number over here or anywhere over here and just do a right click and apply the rule. Now what I can do is just to put, if my A-axis is equal to minus 90, it is legal to use the turning, and I would like to apply the rotation of the 90 degrees. I will apply an additional rule where I will say it's from minus 90, and if it's less of the A and if it's less than the 0, this is illegal. So I cannot use between 0 and minus 90. I will apply additional rule and I'll say, okay, but what if my A-axis is equal to 0? Then I'll say it's legal, but rotate for me the coordinate system for the 90 degrees. Very nice one. And the last condition is, what if it's 0, less of the A and less or equal than 30, which is great because this is the maximum. And I will say this is illegal. Now this is complete definition of what I say about those two rules and how you can apply it. I'll click OK, and if you don't get any error message, it means that you correctly define all possibility rules that could happen, during the definition of the turning operations. Now if I do a double click on the rules itself, here I can apply some mistakes, so just in order to show you what error message will apply. So if I say something like less or equal, which will basically collide with the rule number 4, if I try to hit OK, this error message will apply, which is say, okay, you create the overlap rules, and the rule number 4 and 5 has this overlap, so please change it. So I'll just leave it how it was, and I'll click OK. So this was complete guide how to define 5-axis Mazak i700T for the mill turn. And in this particular case, what I'm gonna do here, I'll just click save. Alright, Now I would like to use this VMID in our project. So I'll just save and exit. And I would like to exit from my project. And I'll go to the SolidCAM settings itself. I'll go to my default CNC controller, and beside of our mill turn y-axis that it was defined, I have also mine that we defined in this tutorial. So I'll just click OK. And I'll now load the same project what we have and using the recent tab. Alright, the last step what you need to do is just to select your particular machine. And let me just show you the rules that we have applied, how it affects actually to our system. So first of all, I'll just open any random turning operation, and over here I have my machine view, so I can go there and click it, and let me go to my 0 degrees over here, and what I have here, it's what is happening if it's A0. If I just try to move with my cursor to the negative direction, you will note that the coordinate system becomes red, which indicates that this is not possible as we actually defined in our VMID. Therefore, I'll just move our coordinate system over here, and I'll apply it to the negative minus 90. And as you can see, the coordinate system changed its position. You can also note that if I say to the 0, the coordinate system is rotated for the 90 degrees. You can't now see it because we don't have any STLs. So let's try to do that now. Alright, to get your STLs in the machine preview, what you have to do is do a right click on the machine itself, and here you can do export to the machine simulation. So what it will basically does, he'll create the XML file into the folder that is selected in the machine simulation name. So I'll just do export to machine simulation, and here we get the information that export was successful. Now before I just set up anything, you have to close your existing machine simulation, and I'll just do an open, and over here we have machine simulation. So of course I will not spend now everything to go into very details, but I'll just like to add few geometries on this project. So first I'll just go to the edit mode, and I'll do a right click over here, and I'll just add the geometries. I'll just go to our folder, and I would like to select the A-axis, maybe something about C-axis, and we can go to the spindle nose, Y-axis, maybe some coolants and so on. I think this will be fair enough. Okay, perfectly. Now all those geometries we just need to put in the correct, I don't need this one. So all those geometries now we have to put in the correct axis. So our A-axis, I'll just cut it over here. I'll just put it over here and just paste it. As you can note, the new feature what we have over here is if you click on the A-axis itself, it will show you the A-axis rotation, positive rotation vector, and this is true. This is the positive one. Alright, so let me go to the C-axis. So both of those, it's on the C-axis, so just do it very quickly. This one, it's on the Z. This one, it's on the X, and this one, it's on the Y-axis. Alright, so and in this point, actually this is a first test to check it out, is our kinematic correctly defined. And the simple way to do that, you can go to the axis control, and you can start with controlling. If the rotation is correct around this pivot point, tilting point, everything is set up well, probably. Also we have the Z-axis, correct limits, Fair enough. Very nice. In this moment, I'll just go to my machine and I'll just hit the save button. I'll go back to my project, L7 exit. What I have to do is go to the SolidCAM itself and reopen this project. This way, the XML file that we just defined with the old geometries inside will basically be loaded in our machine preview. Now the users can use this function. Okay, I'll go to the setup itself, machine preview, and our STLs has been loaded over here, and we can now see everything very nicely. And let me go now to operation itself, to the machine preview. Maybe I can use here calculate in order to bring it over here, and you can note now that the coordinate system is on the X positive, right? Either if it's actually over here, so it's rotated 90 degrees. And as well, if I start to spin it and put it on -90, it will be again rotated. So X will be on up, the same as it is over here in the documentation itself. Hope you enjoyed this video, and see you in the next ones.